Welcome back to Digital Switching Systems 17EC 654 virtual class. Today we will discuss state transition diagrams for N trunks. This is the continuation of mathematical model what we discussed in the last lecture. If we have N trunks to carry the calls, the number of calls in progress varies randomly. It is an example of birth and death process of call and is also called as renewal process. The number of calls in progress is always between 0 and n if we have n trunks. So therefore total is from 0 to n. So we have n plus 1 states and its behavior depends on the probability of change from each state to the one above and to the one below it. And this process or this is called as simple Markov chain. So we'll discuss now what is simple Markov chain and what are its state probabilities and state diagram. A simple Markov chain state diagram is shown in the figure for n trunks, where P of j is the probability of state j and P of k is the probability of the next higher state k, and Pj, k is the probability of state increase to k, that is state transition probability. it gives that the present state is j and it makes a transition to k. Pkj is the probability of decrease to j given that the present state is k. So from k, what is the probability that it will make a transition to j? The probabilities of P of 0, P of 1 and up to P of n are called state probabilities, and the conditional probabilities Pjk and Pkj are called transition probabilities of Markov chain. If there is a statistical equilibrium, which we discussed in the last lecture, that is probabilities remain stationary or stationary random process. If the traffic comes from the stationary random process, then these probabilities do not change and the process is said to be regular Markov chain. These state diagrams represents the trunk states, and each trunk can carry the traffic. Now, if we consider a very small interval of time delta t, starting at some small time delta t, the probability of happening something is very small during that very short period of time. Probability of two or more events happening during a small delta t is very negligible. So, what are the events that can happen during a small delta t? Are first one call arriving with a probability of P of A, or one call can be ended. The call which was going on can end with a probability of P of E, or there is a no change in the state with a probability of 1 minus P of A minus P of E. So these state diagrams represent those trunks and those trunks carry the traffic. We already know that the traffic carried by a group of trunk is given by CH by T. Then the mean number of calls arriving during the average holding time h is equal to c is equal to a. Thus, the mean number arriving during the delta time t is given by a delta t by h. Since this value is very small, a delta t by h will also be very small, and it represents the probability of a, that is one call arriving during the small delta t. So therefore, pjk is equal to P of A, it is equal to A delta T by H, and this value represents what is the probability that one call will be arrived when the trunk is at the state J. If the mean holding time is H and the number of calls in progress is K, one can expect an average number of K calls to end during a period H. So the average number of calls ending during the delta T is therefore K delta T by H. Since t is very small, k delta t by h will also be very small and represents the probability of one call ending during a small delta time t, that is P of E, and it is given by k delta t by h. Now, if the probability of j calls are in progress at the time t, therefore, the probability of trunk being in the state j is given by P of j. Then the probability of transition from j to k busy trunks during the t is given by P of j into P of a. Therefore, the formula becomes P of j into a delta t by h. Similarly, if there are k calls in progress, and then the probability of transition from k to j busy trunks will be equal to P of k into P of E, which is P of k into k delta t by h. Now, if we assume the statistical equilibrium, therefore the state transition probabilities will be equal. That is, P of j transition k will be equal to P of k transition j. Therefore, equating the equation 4 and 5, we get k p of k delta t divided by h will be equal to a p of j delta t by h. Now delta t by h will get cancelled. Therefore, p of k will be equal to a by k into p of j. Now if we substitute the values for k, p of 1 will be equal to a by 1 p of 0. Similarly, p of 2 will be a by 2 into p of 1. If we continue like this, we get the formula p of x will be equal to a square divided by x factorial into p of 0. Therefore, in the last slide, we saw the equation p of x is equal to a to the power of x by x factorial into p of 0 using statistical equilibrium. Now, the assumption of pure chance traffic implies a very large number of sources. Thus, x can have any value between 0 and infinity, and the sum of their probabilities must be unity, because sum of all probabilities should be equal to 1. Then 1 will be equal to summation x to x from 0 to infinity p of x will be equal to summation x is equal to 0 to infinity a to the power of x by x factorial into p of 0. Therefore, therefore this summation should be equal to 1, and this will be equal to e to the power of a into p of 0. Therefore, p of 0 will be equal to e to the power of minus a. Now, substituting p of 0 is equal to e to the power of minus a in the previous equation, we get the equation of for p of x, which will be equal to a to the power of x by x factorial into e to the power of minus a. So, this is the equation for the probability of number of calls arriving, which follows the Poisson distribution. P of x will be equal to e to the power of x by x factorial into e to the power of minus a. Thus, if call arrivals have Poisson distribution, so does the number of calls in progress. For this condition to happen, we require infinite number of trunks to carry the calls. If the number of trunks available is finite, then the some calls can be lost or delayed, and the distribution is no longer Poissonian. That is what we saw in the last lecture, that the number of calls going on and the number of transition in between interval follows the negative exponential distribution. So we have discussed the state transition diagram or the Markov chain, which you already know from various other subjects from digital electronics to ITC, which you have used the state transition diagram tables and Markov chains, that has been applied to traffic congestion or the number of calls which are handled by the trunks. So we understood that, and later we derived how the probability of number of calls arrival follow the Poisson distribution, and we got the Poisson distribution p of x will be equal to a to the power of x by x factorial into e to the power of minus a. So thank you for watching.